Dear students, today we start our new course, that is Algebra 2. Course code is Math 315. This course is about ring theory. Before discussing what a ring is, let's recall few concepts you already know from our previous courses. So the first concept we are going to define is binary operation. And you know about binary operations very well. For example, addition is a binary operation in the set of real numbers. Addition is also binary operation in the set of integers. Similarly, multiplication is a binary operation in the set of real numbers. Multiplication is a binary operation in the set of integers as well. So we give the formal definition, binary operation. So definition goes as follows. Let S be a non-empty set. Then a binary operation in S. Then a binary operation. In S is a function. We represent this function by star. So binary operation is a function star from S cross S into S and is given by, if we are given any element of S cross S, let's say AB, this order pair belongs to S cross S, then under this binary operation, this order pair AB will go to A star B. So A star B would be an element of the set S. Hence, you can see that under this definition, or according to this definition, addition is a binary operation from set of real numbers. Similarly, addition is binary operation in the set of integers. So let's take another note. So we also say that star is a binary operation defined in S. Star is a binary operation defined in S. Condition is if A star B exists and A star B belongs to S. This is for all AB belonging to S. Thirdly, we also say that if A star B belongs to S, for all AB belonging to S, then S is closed under star. S is closed under star. अभी कुछ बुक्स जो है ना यूज़ करती हैं द सेट इज़ क्लोज्ड अंडर दैट पर्टिकुलर बाइनरी ऑपरेशन. कुछ बुक्स कहती हैं that particular binary operation is defined in the set. तो मैंने ये दोनों बातें लिख दी हैं. So let's come to another definition, and you know it very well as well. What is associativity? So let's define that. This is about associativity. So a binary operation star defined in S, a binary operation star defined in the set S is said to be associative if condition is that if A star B star C is equal to A star B star C, and this is for all A, B, C belonging to S. Note that A star B star C, B star C is in the bracket on the left hand side, while on the right hand side A star B is in the bracket and then A star B star C. So this is associative law. Next we come to commutative law, and you know this law as well. So let's define it formally. Definition. This is about commutativity or commutative law. So a binary operation star defined in set S is said to be commutative. A binary operation star defined in a set S is said to be commutative if the condition is that A star B is equal to B star A for all A, B belonging to S. So this is definition of a binary operation being commutative. And you know that addition is a commutative binary operation in the set of real numbers. Similarly, multiplication is also a commutative binary operation in the set of real numbers. Let's recall a few more definitions. So let's define what an identity element is in a set S. For example, you know that in the set of real numbers, if we consider the binary operation addition, then 0 is the identity element in the set of real numbers with respect to addition. And if you consider multiplication, then 1 is the identity element in the set of real numbers with respect to multiplication. So let's define it formally. So definition. This is about identity. So let star be a binary operation in the set S. Let star be a binary operation . in a set S, then an element we mostly represent this element by E, then an element E belonging to S is called identity element in S, is called identity element with respect to, so WRT, this is with respect to star, binary operation star, if A star E is equal to E star A is equal to A, and this is for all A belonging to S. So this is the definition of identity element in a set S. Now we come to definition of inverse of an element. So next definition, this definition of inverse. So definition goes as follows. Let star be a binary operation defined in the set S. Let star be a binary operation defined in a set S. अब चाहे तो you can simply say that star is a binary operation in the set S or in a set S, or it is better to say that let star be a binary operation defined in a set S. So let star be a binary operation defined in a set S and E belonging to S be the identity element in S with respect to the binary operation, whatever we are considering. In our case it is star. So let E be the identity element in S with respect to this binary operation star. Let A be an element of S. Let A belong to S, then an element B belonging to S is said to be inverse of A if the condition is if A star B is equal to B star A and this is equal to identity element E. So if this happens, then we call that B is inverse of A. So if this happens, then we say that B is inverse of A. Note that we usually write A minus 1 for inverse of A. Therefore, this particular condition becomes, therefore above condition becomes instead of B we will write A minus 1. So this condition becomes A star A inverse, we call it A inverse, is equal to A inverse star A is equal to identity element E. So this is definition of inverse of an element. Having said that, we know that what is definition of a group. So let's define a group. So definition, let G be a set together with the binary operation star defined in G. Let G be a set together with the binary operation star defined in G such that first of all, associativity. So what we mean is that A star B star C is equal to A star B star C. And this is for all A, B, C belonging to G. This is the first condition. Second condition is existence of identity element. So existence of identity. And this condition says that there exists an element E belonging to G such that A star E is equal to E star A, and this is equal to A for all A belonging to G. So this is existence of identity element. And the third condition is existence of inverses. Existence of inverses. So condition for existence of inverses is that for any A belonging to G, for any A belonging to G, there exists an element, let's say call it B, B belonging to G, such that A star B is equal to B star A, and this is equal to identity element E. We call this element B as inverse of A. If this happens, then B is called inverse of A. And we mostly write A minus 1 for inverse of A. So this was the condition for inverse, existence of inverse. So these conditions, first of all, associative law. First of all, there has to be a binary operation defined in G, or G has to be closed under the binary operation star. Secondly, the operation has to be associative. Then there must be an identity element, and then inverse of each element must exist in G. So with all these conditions, we say that G is a group. So if G satisfies all these conditions, then G is called group. Then G is called group. Let's have another definition, and that is about abelian group. And you know that if the binary operation is commutative, then the group is called abelian group. So our next definition is for abelian group. Definition of abelian group. So if G is a group under binary operation star, if G is a group with binary operation star, then G is said to be an abelian group. Then G is said to be abelian group, or commutative group. Let me write it in bracket, or commutative group. If the condition is A star B is equal to B star A for all A, B belonging to G. So this means that the binary operation is commutative in the group G. So this is definition of abelian group. So having said that, let's recall some examples of groups. Your previous course was about group theory, और आपको याद होगा आपने बहुत सारे ग्रुप्स जो हैं वो स्टडी कर रखे हैं. So before giving examples, let's note that for abelian groups, the binary operation is mostly denoted by addition. So let's have this note. For an abelian group G, the binary operation is usually denoted by the symbol this symbol which is used for addition. So if a group is abelian, then the binary operation is addition, and the identity element is written as the symbol 0. Also, the inverse, in fact, we call it additive inverse, and the inverse of an element A belonging to G is denoted by minus A. So all I am saying is that if group is a abelian group, then we write this symbol plus for binary operation, and for identity element we write 0, and for inverse of an element A we write minus A. जैसे आप जानते हैं कि सेट ऑफ रियल नंबर जो है वो अंडर एडिशन ग्रुप बनाता है, और इस ग्रुप में अंडर एडिशन जो आइडेंटिटी एलिमेंट है वो 0 है, और अगर आप 6 का इन्वर्स लेना चाहें एडिटिव इन्वर्स रिस्पेक्ट टू एडिशन, तो उसे हम -6 लिखते हैं. सो हैविंग नोटेड दिस, let's discuss few examples of groups. Examples of groups. तो ये सब एग्जांपल्स आपने काफ़ी डिटेल में आपने अलजबरा 1 के कोर्स में कर रखी हैं. द फर्स्ट, द सिंपलेस्ट एग्जांपल इज R the set of real numbers is a group under addition. Z the set of integers is a group under addition. Q the set of rational numbers is a group under addition. So let me write all these examples. R the set of real numbers, Z the set of integers, the set of integers, and Q the set of rational numbers, the set of rational numbers, and C the set of complex numbers, and C the set of complex numbers. These are groups under binary operation addition. Under binary operation addition. And note that all these groups we have written are abelian groups. These are abelian or commutative groups. So these are abelian groups. In fact, infinite abelian groups. So these are abelian groups. So having discussed this particular example, that set of real numbers, set of rational numbers, set of complex numbers, set of integers, these are abelian groups under binary operation addition. A very famous example of a group is the dihydral group. Dn, the set of symmetries of a regular n-gon, a regular polygon with n sides. So Dn, the set of symmetries, and you know what symmetries we mean. Symmetries means rotations and reflections. Rotations and reflections. So Dn, the set of symmetries of a regular n-gon a polygon with n sides, n equal sides in fact, of a regular n-gon is a group. This is called the Dihydral group. And you know that this is a non-abelian group. This is non-abelian group. We come to next example, and you know that the set of permutations on n elements is a group. You call it the symmetric group. This is again non-commutative. So Sn, the set of permutations on n elements is a group called symmetric group. This is non-abelian again. So this is non-abelian as well. So the set of permutations on n elements is a group, and this is a non-abelian group. Next, we discuss the groups of the form Zn. Zn we mean 0, 1, 2, 3, so on up to n minus 1. If it is Z6, then this is 0, 1, 2, 3, 4, 5. If it is Z7, then this is 0, 1, 2, 3, 4, 5, and 6. So Zn is group under binary operation. You know this binary operation. This is addition modulo n. Under addition modulo n, this is group, and this is abelian group. In fact, this is not only one group, these are many groups. So for each n you obtain such a group. So these are abelian groups. And then we come to next group. You know that if you take a set of matrices of same order, then addition is defined, zero element is there, inverses are there, everything is there. So let's note this particular group. Let's represent it by capital M, and then write here M cross N. This means this set of matrices with order M by N. So M cross N, the set of matrices of order M by N with real entries. Real entries means elements in entries of each matrix will be real numbers. So with real entries, so the set of matrices of order M by N with real entries is a group under addition of matrices. Is a group under addition of matrices. Our next example is, now we consider the set of non-singular square matrices with real entries. This is a group under multiplication. So before going to next example, let's note that this particular group, this is a abelian group. The group we have discussed, M cross N under addition, this is a abelian group. The next we are going to discuss is not abelian. So let's discuss the next group, Mn. Mn means the set of non-singular matrices of order n cross n, square matrices. The set of non-singular, it is very important to note that non-singular. So the set of non-singular matrices of order n by n. So saying n by n means that these matrices are square matrices. So anyway, when we talk about non-singular matrix, it is always a square matrix. So the set of non-singular matrices of order n by n with real entries, mean the entries of each matrix consist of real numbers. So Mn, the set of non-singular matrices of order n by n with real entries, is a group under multiplication of matrices. Is a group under multiplication of matrices. And this group is non-abelian. This is not only one group, these are many groups. In fact, for each natural number n, you will get such a group. So these groups are non-abelian. For, to be very precise, we must say that for n greater than or equal to 2, because for n is equal to 1, this is just a trivial case. So these are non-abelian groups. So Mn, the set of non-singular square matrices, is a non-abelian group. So let's come to next example, and this is a very simple example. Note that Let's write R for the set of real numbers. Let R be the set of real numbers. Then अगर हम R में से ज़ीरो एलिमेंट निकाल दें, R में से ज़ीरो एलिमेंट निकाल दें, तो then R minus ज़ीरो is a group under multiplication of real numbers. Under multiplication. And similarly, अगर आप सेट ऑफ रैशनल नंबर्स में से ज़ीरो एलिमेंट निकाल दें, और इसी तरह से अगर आप सेट ऑफ कॉम्प्लेक्स नंबर्स में से ज़ीरो एलिमेंट, ज़ीरो कॉम्प्लेक्स नंबर होता है, ज़ीरो प्लस आइटा ज़ीरो निकाल दें, आर आल्सो ग्रुप्स under multiplication. And these groups are abelian groups. So our next example, you know it very well, that is clean 4 group. So G consisting of 4 elements, E, A, B, C, where A square is equal to B square is equal to C square is equal to E, and E is identity element. And E is identity element. Is group, and you can easily construct the Calais table for this particular group. And you have done this group when you are studying Algebra 1. So having said all these things, now we come to another concept, and that is distributive law. Note that so far we have discussed only one binary operation on a set, and for that binary operation the properties we have discussed are commutative property and associative property. There is another property we know very well about from our experience of working with real numbers, and that is called distributive property. So for defining this property, distributive property, so let's say we are going to discuss second concept now. So we frequently come across sets in which two binary operations are defined. So we frequently come across sets in which two binary operations are defined. फॉर एग्ज़ाम्पल सेट ऑफ रियल नंबर्स में आप जानते हैं एडिशन भी डिफाइंड होती है, मल्टीप्लिकेशन भी डिफाइंड होती है. सो इसी तरह सेट ऑफ इंटीजर्स में एडिशन भी डिफाइंड होती है, मल्टीप्लिकेशन भी डिफाइंड होती है. सो फॉर एग्ज़ाम्पल वी कैन कंसिडर दिस एग्ज़ाम्पल. Consider Z the set of integers, so consider this particular set. This is a set of integers, and we know that addition is a binary operation in Z, and Z is a abelian group under addition. And we know that addition is binary operation in Z, and Z is a abelian group under addition. So we know this thing very well. Addition is in fact defined, and Z is abelian group under addition. Secondly, this is our first observation, and secondly, multiplication is an other binary operation defined in Z. You know that multiplication, 2 multiplied with 3 is equal to 6, 6 is there. 2 multiplied with minus 2 is minus 4, minus 4 is there somewhere. So multiplication is an other binary operation defined in Z, and you know it very well, defined in Z. And about this binary operation, we know that which is associative. Multiplication in the set of integers is associative, which is associative. That is, when we say associative, this means that A star or not star in this case, our operation is multiplication, and you know that when we work with multiplication, mostly we don't show this symbol, we use the notation of juxtaposition. तो हम ये सिंबल लिखते नहीं है, लेकिन हमें पता होता है कि multiplication is there. So associativity will be written as A multiplied with product of B and C, and this is equal to product of AB multiplied with C for all ABC belonging to Z. So multiplication is associative in the set of integers. So this is our second observation. Now note about third observation, that addition and multiplication together obey two laws in Z. So let's discuss about these laws. So addition and multiplication together ये प्रॉपर्टी जो है, ये ऐसी प्रॉपर्टी है जिसमें ये दोनों ऑपरेशन इस्तेमाल होते हैं. सो एडिशन एंड मल्टीप्लिकेशन टूगेदर ओबे two laws in Z, and these laws are और ये laws आप खुद पहले से जानते हैं. We call left distributive law and right distributive law. So left distributive law, which says that A multiplied with sum of B and C is equal to A multiplied with B plus A multiplied with C. So this is left distributive law. This is for all A, B, C belonging to Z. And secondly, this is right distributive law. And right distributive law says that B plus C multiplied with A is equal to B multiplied with A plus C multiplied with A for all A, B, C belonging to Z. Just have a note that we know that in set of integers multiplication is commutative. So left distributive law and right distributive law, in fact these are same laws. But if multiplication is not commutative, then these two are different. We have to note this very carefully. In Z, the multiplication is commutative. The multiplication is commutative. Therefore, the above laws are same. However, if we are working with a structure which has non-commutative multiplication, however, if we are working with non-commutative multiplication, then above laws are different and need to be dealt carefully. Suppose if we are working with matrices, then multiplication of matrices is non-commutative. So in such cases, we have to be very careful. So having discussed these concepts, note that what we have discussed in this particular section is that we have discussed Z, and we have noted that Z is an abelian. First of all, note that in Z we have two binary operations defined. One is addition and the second is multiplication. Under addition, Z is an abelian group. For multiplication, we have noted that multiplication is defined in Z, or you can say that Z is closed under multiplication. Secondly, multiplication is associative in Z. And thirdly, we have noted that addition and multiplication together satisfy two laws. One is left distributive law and the second is right distributive law. So all these conditions